Welcome and thank you for joining. I am Bennett Akmamadaye. I'm presenting our research on defending against object misclassification in smart vehicles through adversarial training. We address defending against adversarial attacks to ensure reliable object classification, and I'll cover our training algorithm, environmental setup, our results, highlighting the impact on autonomous driving technology as regards this research. Here is an overview of today's presentation. First, we'll start with an introduction to set the stage ruling, and then we'll provide background and context of our research. Also, we'll define the objectives of our study, then discuss the system model that was used. Then we'll look at outlining our methodology. Then we'll present our experiment analysis. Then we'll share the results that we achieved and engage in a short discussion of our findings. Then finally, we'll conclude on summarizing our work with the conclusion. Adversarial attacks pose significant threats to the security of machine learning systems, and particularly in smart vehicles, which we'll be looking at. It's good to know that these attacks cause misclassification of objects, potentially compromising the safety of autonomous driving system. And for us to be able to tackle this challenge, it's good to understand that researchers and also security experts have explored various defense systems with adversarial training, which emerging as a promising solution. Looking at our background and context, adversarial training has emerged as a promising defense mechanism, enhancing model robustness by incorporating adversarial examples into the training of data. However, it is good to note that research on adversarial attack and defense methods, especially in the digital domain, still very limited. This our study aims to investigate the efficacy of adversarial training in defending against misclassification in smart vehicles. The core problem we intend to address is how adversarial training can be utilized to prevent misclassification of objects in smart vehicles. Our research aims to explore and demonstrate the effectiveness of adversarial training as a defense mechanism in enhancing the accuracy and reliability of object detection systems in autonomous vehicles. Our study has three primary objectives. The first will be demonstrating the potential of adversarial training as an effective defense mechanism against object misclassification in smart vehicles. Also, we look to enhance the reliability and safety of smart vehicles by reducing the occurrence of misclassifications. And finally, we look to contribute to ongoing research on adversarial attacks within the smart vehicle domain. So, looking at our system model, we would follow a structured approach. First is to pre-process the data, which entails preparing the data set for training, and then we build our CNN model. We'll look to develop a convolutional neural network model for this system, and then we train the model on data sets. So we train the CNN using the prepared data set that we currently have, and then also we'll look to evaluate the accuracy on the test data set that was used. So that entails measuring the model's accuracy on the test data set. And then we apply the FGSM attack, which is the fast gradient method. We look at implementing the fast gradient sign methods as the attack approach. Then we evaluate the accuracy on the attack. So this simply entails assessing the model's accuracy under the given attack. Then we compare accuracies. This entails comparing the accuracy results before and after the attack. And finally, we analyze the results of both the original and perturbed image. Looking at our methodology involves using a convolutional neural network model designed with the following structure. We have a conv2D and max pooling 2D layers. These layers extract the features from the 200 by 200 RGB images. Then we have the flattening layer and the dense layers. After this extraction, the flattening layer and dense layers are then used for the classification. And looking at the feature extraction, the conv2D layers create filters, while the max pooling 2D layers reduce the spatial dimensions in this. And then finally, we look at pattern refinements. The dense layers, including one with 64 neurons, further helps to refine the patterns. Then finally, the final dense layer has 10 neurons, which helps in outputting probabilities for the 10 classics suitable for multi-class classification of our tasks. And looking at our model training, the fit method was used to train the model. We had the train and test generators provide batches of training and validation of data. Then also the training duration was we used 22 epochs to train the model. And then we looked at our loss and accuracy metrics. The training loss and accuracy were computed and the training data was read. And also looking at the validation loss and accuracy, we calculated that on the validation data. Then the training objectives of this research was to minimize both loss values while maximizing accuracy. High accuracy and low loss indicates good performance on the training data. Then, in terms of our experiment analysis, we utilize the cargo traffic sign data with about 5,911 training data sets and 324 test images across 10 classes. This was supported by a class description CSV file. The data management was streamlined using Google Drive on Colab, and the images were standardized to 64 by 64 pixel, helping us to optimize training efficiency with a batch size of 32. And also, further to drive, data augmentation was done using the image data generator, and this enhanced training data diversity with techniques like we had the rotation, the shift, and sharing. Separate generators processed augmented batches for training and testing data sets. The sequential model featured convolutional and also max pooling layers for feature extraction, like I said before, and this was followed by flattened and dense layers for classification. Like I said before, the training span 22 epoch with the Adam optimizer and categorical cross entropy loss to optimize performance and combat overfitting in our model for us to be able to get the required results. And looking at the FGSM attacks that was used before, which is the fast graded sign method, it helps to generate the adversarial examples by adding small perturbations to input data, and this inducing the mixed classification. Like the formula given, it helps to compute the perturbed input swiftly, and utilizing these model gradients and also a specified epsilon for this attack. The FGSM quickly modifies the input images to maximize loss, highlighting its efficiency in the adversarial training. And then when you iterate over the batches of the test images, the our code applied the FGSM attack with varying epsilon values and generating these adversarial examples. It was stored in list. These examples are then concatenated into a TensorFlow tensor. Now, when you do this, it assesses the model's vulnerability. Then visualizing both the original and the perturbed images allows comparison for us to be able to highlight the impact of adversarial perturbations on the model predictions. And it goes on and follows the same procedure. Now, looking at our environment and tools, for this research, we use the Google Colab environment, which is a cloud-based platform that integrates with Google Drive, where we store the data set, and it was easy for us to call up the data sets on Google Colab. So this just ensures that we have efficient use of our hardware. Then also TensorFlow and other related libraries were facilitated to develop the model, also train and then evaluate for us to be able to provide a robust framework for deep learning tasks. Looking at our results, after computing and then moving to the use of the FGSM method, at the time we used an epsilon value of 0.007. The input image perturbations were minimal, and then it helped to create mild adversarial examples. The model achieved a perfect accuracy of 1.0 on these examples, and this showcases the robustness against perturbations around 0.007 after training. Then also looking at raising the bar, we raise the epsilon to about 0.01, and this results in a slightly larger perturbation. Although still small, these perturbations become more noticeable, causing the model's adversarial accuracy to decrease to about 0.75. And then we further look to raise the bar, and we increase the epsilon to about 0.02, which resulted in a decrease in the adversarial accuracy to 0.5. Now, this shows that the more significant perturbations they will end up successfully deceiving the model, and this would potentially cause misclassification. Now, looking at the results in general, when the epsilon was about 0.007, the perturbations were minimal, and the model's accuracy on these adversarial examples was perfect at 1.0, and further increasing to about 0.01 caused it to slightly increase. And then when we further, and the result further reduce the accuracy to 0.5, then when we further increase the epsilon to about 0.02, this resulted into significant perturbations, and it dropped the accuracy to about 0.5. This indicates that when the value of the epsilon is increased, it's the system is increased to susceptibility of misclassification. Now, looking at it holistically, with the epsilon values that we have and with the accuracies of 1.0, 0.75, and 0.5 respectively, this shows that the model is resilient to very minor perturbations, and it will maintain accurate object classification under these mild adversarial attacks. Adversarial training can then focus on how these mild perturbations would ensure robustness in real life scenarios. So looking at it this way, it simply means that we can be able to get misclassification under the mild perturbations. But when we begin to increase the epsilon, and then we need to understand that we need to train these models to be able to withstand moderate perturbations or even higher ones. And will be common in this will be common adversarial attacks that could cause misclassification. Now, this underscores the importance for us to now develop robust defense mechanism to handle very severe attack, which will pose serious safety to life and also cause risk for smart vehicles on our roads. In order to sum up, overall, our study highlights that adversarial training is an effective defense against object misclassification in smart vehicles. The model showed resilience to minimal perturbations and maintained a high accuracy even with very mild attacks. So this shows that there's the importance of incorporating adversarial examples in training to enhance model robustness. But however, there is a need for continued research and also collaboration between industry giants, regulatory bodies, and also academia for us to be able to advance adversarial defense mechanism, because this seems to be a promising approach. So the more we can understand and further delve into this part of our work, the better it is for us to be able to get good results and see how we can help the smart vehicles domain. Thank you so much for listening, and have a great day ahead.